Hmm. Okay, the plan for today is to finish section 3.2, start and finish, hopefully, section 3.3, and possibly get started on chapter 4, probability. I think we're running a little bit behind schedule, but that tends to happen in the beginning of the semester. There's just so much material in the first couple of chapters, and then things kind of smooth out as we start moving along. So, so long as we don't have any class cancellations or snow days or anything, we should we should be on track pretty soon here. But even if we do have a cancellation, we have some built-in um, just like margin days, kind of study days. So um, one quick note, I ha actually have to cancel class on Wednesday. So this coming Wednesday, a couple of days from today, I have a doctor's appointment. I just can't move, so I need to cancel class that day. But I will post a supplemental video this afternoon. So depending on how far we get today, I'll probably just post a previous semester's class recording, uh, from what will most likely be the start of the chapter 4 material, but we'll see where we get to today. And that will be up this afternoon, so you can view that in lieu of coming to class on Wednesday. So, and of course, if you have any questions, feel free to pop in office hours, send me an email, anything like that. And I will send out a Blackboard announcement probably Tuesday night as well, just as a reminder, but just letting you know so that you can plan ahead. The other big administrative thing we have coming up pretty soon here is Unit 1 exam is next week. So not the week that we're in now, but the following week. Everybody uses the words next week a little bit differently, I think, but so not the week that we're in now, but the week upcoming. The material is on chapters 1 through 3. The time allotted is an hour 40 minutes. And note that you can only take the exam once. You only get one attempt per problem, so a little different settings than the homework. The homework sets, of course, um, and the exam must be taken during that week. So it must be taken from Monday, whatever it is, a week from today, I guess the 24th at 9 a.m. through the following Sunday at 11:59 p.m. The dates and everything are on the syllabus. They'll also be on the exam when it's available. Uh, as I mentioned, I have some typos here. As I mentioned, no ProctorU being used for the exams. So I talked a little more extensively about that in a past lecture. So, but we're not using ProctorU, so you'll sign on, take the exams, in a similar manner to how you do the homework. There was one more thing I wanted to say about exams. Oh, yeah. There's material posted in supplemental materials folder. Some of it is material related to the class that I've just made available, but there's also this exam 1 formula sheet that you might find helpful to use on the exam. So, so take a look at the exam 1 formula sheet. You can use it as a PDF. You can print it out and use it, in hard copy form. You can have one of each if that, if that works better for you. You can also make your own formula sheet if you prefer that, but there's one that's kind of, ready to go for you. You can use calculator, handheld calculator. You can use Excel/StatCrunch. So that technology can be used on the exam, but of course, no other people, no like Googling things, anything like that. And then, very important, maybe I'll actually bold this. Do not wait until the last minute to take the exam. I would recommend planning to take the exam on or before Thursday night next week. So not this week again, next week, but plan to take it on or before Thursday. It's due Sunday. That way, if you log on Thursday night and whatever, the power goes out or your internet's not working or there's some kind of technical glitch that your computer is not wanting to cooperate, there's still plenty of time to get that worked out, to reach out to me, to reach out to tech support, to get things figured out, possibly find a different venue, go onto a campus or something instead of taking it home or vice versa. There's time and flexibility um, to kind of come up with alternate plans or to get things worked out. if you wait until Sunday evening or Sunday night to take the exam, number one, not a lot of things are open on Sunday. You're not going to be able to go to a library if you need to, if your internet's not working or something. Also, it's just more stressful if you know that you have no margin built in. So for the benefit of the extra couple of days of study time, it's probably not worth the risk, right? That's a pretty significant trade-off, pretty significant risk that if anything goes wrong, you can't take the exam and you lose out on all of those points, for the final course grade. So definitely recommend planning to take the exam Thursday night at the latest. Oh, and that was what I wanted to mention that I think I had skipped over. The sample exam is available now, so you can find it at the top of the assignments page on my stat lab. And the sample exam is quite similar to the actual exam. So exams I always post at the top of the assignments page, just so they don't get jumbled in with assignments and all of that. Our most recent assignments are at the bottom of the assignments page. And this way it's just easy to find. Exam is already a little bit of a high stress time, so you can go to the assignments page and it's kind of right there for you at the top. So just so you know where it's located, the sample exam is available now. You should see it on my stat lab. The actual exam won't show up. It won't be available until Monday at 9 a.m. So that week that it's set to be available. And the other unit exams and the final exam will work very similarly to all of this. All of these general ideas will be the same for them. The time for the final will be 2 hours instead of an hour 40. The material will, of course, be a bit different, but the rest of this will be pretty similar. Any questions about the Unit 1 exam coming up?
Yeah, I had two questions. One is the test found on my stat lab, and then the other is once we're done with the test, is it graded right then and there?
Yeah, good question. So yes, it is. So the sample exam is on my stat lab right now on the assignments page, and when we hit next Monday at 9 a.m., the actual exam, the Unit 1 exam, will be like right just above or just below the sample exam on my stat lab on the assignments page. Um, yeah, and great question. So with grading, my stat lab obviously automatically grades things like you've seen with the homework, and it will do the same for the exam. After all of the exams are due, so after the due date for the exam, so depending on when you take your exam, that might be a little while after you've turned yours in. That might be several days. But after everything is after the due date, after everybody has turned in their exams, I'll manually go through and check any problem that my stat lab has marked wrong. I'll check and make sure that it's actually wrong. Um, so I'll go through and add full credit for things that maybe it's just a syntax issue or something like that, or a funny typo or something like that uh, that is clearly correct, but my stat lab just didn't know how to parse correctly. And I'll give partial credit for things that warrant partial credit. Partial credit will be pretty limited, but I will give partial credit based on the answers on my stat lab. I don't give partial credit based on any work in remote classes. That's just a bit of the trade-off with remote classes. It's already challenging enough technologically, especially when we have proctoring going on, just to make all of the tech for the exams work out. If you try to layer on top of that additional tech for, submitting scratch work or anything like that for partial credit, that's just so much more complexity, so many more things that could fail. So for remote or online classes, I don't take scratch work for partial credit, but I do give partial credit based on the answers submitted. And I also do adjust the problem types and the difficulty level of the test in light of the fact that there's not going to be partial credit for scratch work. So I do definitely take that into account, right? These wouldn't be the carbon copies of the tests that I would give, say, in class course, where I would be giving some additional partial credit for things like scratch work. So in those classes, there would tend to be far fewer number of questions. They would be longer, more extensive, more complex. So it would be a more difficult exam in some respects, but then also, you would be getting partial credit for scratch work. But for online and remote classes, I only base partial credit on the answer submitted. Yeah, good questions. Any other questions
Good.
about the exam?
Thank you.
Yeah, sure. Okay. And then last, our quote of the day, really quick. Um, this is by composer Hans Zimmer. He writes musical scores for major movies. I think he was the Dune guy. I think he did Dune recently. Um, but he's a big name, kind of like John Williams, probably second to John Williams. I don't know. Um, but I was watching an interview with him once, and he said something that I thought was a really interesting quote. He said, "At my best, words will fail you because I'm using my own language." And the interviewer, I think, was asking him a question, something like, "How would you describe your music?" or something, and this was his response. And I think that really gets at the heart of uh, many of the kind of humanities, many of the aesthetic humanities, things like the arts, right? Music uh, or even in a sense, poetry or something like that, even though they're kind of using our language, but um, or so music or drawing or painting or poetry, things like that. Um, they're kind of exploring ideas that we find difficult or maybe impossible to actually put into words very clearly and very concisely. They're almost operating at the edge of human understanding. So sometimes that can just look, a little bit nutty, and you're like, what are you doing there? And other times it's, well, I really like that, but I don't know why I really like that. I can't put it into words. It's almost like if I could put it into words, it wouldn't be great art. Almost there's a saying that goes something like a good book resists summarization, you know, and in some sense, like writing a book report or writing a summary of a book kind of does discredit to a book. It's like, well, if you could say in 2 paragraphs what this author has taken, 600 pages to say, well, they probably should have just written 2 paragraphs, right? Um, so anyway, that's the quote of the day, the thought of the day, by Hans Zimmer. Okay, so wrapping up just the tail end of 3.2, taking a quick look at Chebyshev's theorem. Um, Chebyshev is a Russian guy, a Russian mathematician from I think early 1900s. First name Pafnuty, cool first name. Um, and his name is translated in probably a dozen different ways, so or transliterated, I suppose. This is the way I chose to transliterate it. Sometimes you'll see a V at the end. Sometimes you'll see like TCH at the beginning. So there's all kinds of different ways people spell it. So our book might spell it differently. I'm not sure, but if it's something like Chebyshev's theorem, this is the theorem. And it says, so just a really quick note, recall from last week, it has been 5 days. So recall the empirical normal rule that said if a data set is bell-shaped, if it has this kind of bell-shaped or normal distribution shape to it. Sorry, my allergies are just absolutely driving me crazy this morning. We have a mean, and we have a standard deviation. Going from mu minus a standard deviation to mu plus a standard deviation. So a mean plus or minus one standard deviation. If our data set is bell-shaped, this should comprise about 68% of our data points. 68% of our data points should be within one standard deviation of the mean. 95% within 2 standard deviations of the mean, and 99.7% within 3 standard deviations of the mean. Or another way of looking at this is to say that a 1 sigma event should occur maybe 1 out of 3 times, about 32% of the time. That would be a data value that's more than 1 standard deviation away from the mean. That's what we call a 1 sigma event. Or a 2 sigma event should occur about maybe 1 out of 20 times, about 5% of the time. About 5% of our data points should have a value that's more than 2 standard deviations away from the mean. Again, if our data set is roughly bell-shaped. And three sigma events should occur about 1 time out of every 300, or about 0.3% of the time. So that would be the proportion of data points whose values would be more than 3 standard deviations away from the mean. And the huge caveat here is if the data set is roughly bell-shaped. It's a very important caveat. Now, we often encounter data that are roughly bell-shaped, so this isn't kind of an off-the-wall assumption, but it is an assumption nonetheless. Chebyshev's theorem says something similar to the empirical normal rule, but the important thing is this works for any data set. This is based on the underlying mathematics of how things like standard deviation and mean are computed. So for any data set, the proportion of data points whose values fall within k standard deviations of the mean is at least 1 minus 1 over k squared for k bigger than 1. Or another way of saying it is less than 1 over k squared data points have a value more than k standard deviations from the mean. So let's look at k compared to 1 minus 1 over k squared. Well, for k equals 1, note that our theorem doesn't apply. So we're looking to kind of compare with our rules up here. For k equals 2, I have 1 minus 1 over 2 squared. 1 minus 1/4 is 3/4, or 75%. And for k equals 3, I have 1 minus 1/9, or that's 9 minus 8 over 9. That is 9 minus 1 is 8 over 9 is about 8/9 is about 89% or so. So if we know our data set is bell-shaped, we know that about 95% of our data points are within 2 standard deviations of the mean and about 99.7% within 3 standard deviations of the mean. But if we don't know anything about our data set, or we don't want to assume anything about our data set, instead of saying we think that about 95% will be within 2 standard deviations, we know that at least 75% will be within 2 standard deviations. Instead of saying that we think that about 99.7% will be within 3 standard deviations, we know that at least 89% or so will be within 3 standard deviations. Sorry, give me 1 second here. All right, sorry about that. My allergies, these aren't this bad, especially in the winter, but I don't know what it is today. Or maybe I'm doing the guy thing and saying it's allergies when I'm actually starting off a cold. Hopefully not. Okay, so we see that Chebyshev is much more conservative, right? It's estimating guaranteeing a much lower proportion of data points that have a value within, say, 2 or 3 standard deviations of the mean than the empirical normal rule. So it's in some sense making less of a strong claim in that sense. However, the thing about Chebyshev is, again, it works for any data set. We have no assumption made on the shape of the data set. Or another way of saying it is, what's the probability of a 1, 2, or 3 sigma event? What's the probability that a data point is more than 1, 2, or 3 standard deviations away from the mean? Again, k equals 1 doesn't apply. Chebyshev applies for k strictly bigger than 1. But we see that Chebyshev for k equals 2 would say 1/4 or 25%. And for 3 standard deviations would be 1/9 or about 11%. Again, remember that the empirical normal rule says 5% chance of a 2 sigma event. Chebyshev is saying no more than 25%. Empirical normal rule is saying 0.3% chance of a 3 sigma event. And again, Chebyshev is much more conservative, saying no more than 11%. Right, so we're a whole 2 orders of magnitude just about off on the 3 sigma event side of things, and about maybe 1 order of magnitude or so off on the 2 sigma event side of things. So one characteristic of the bell-shaped distribution isn't simply that it tails off to the sides, but it actually goes to 0 out here very quickly. These tails get very small very quickly. But Chebyshev has to work for any data set, and this is the claim that it makes. Now, one little note, we're not going to prove this at this point, but we will actually prove this a little bit later in the course. So once we've built up a little more notation and understanding from chapters 4 and 5, we will come back and we'll prove a couple of these theorems that we've discussed so far. So we're punting this until a little bit later, the proof of Chebyshev's theorem. But so on one hand, Chebyshev's theorem doesn't seem like it's super useful. I mean, it's, in most cases, way too conservative to be really useful. But one of the things that Chebyshev is really useful for is it provides the foundation on which a lot of the important theorems, so like, for instance, the central limit theorem, some of these kind of ideas are based on. So it's really providing some of that theoretical basis for some of the more important theorems. So that is Chebyshev's theorem. And that wraps up section 3.2. Any questions on 3.1 or 3.2, measures of center or measures of variation? Okay, so jumping into 3.3, measures of position or measures of relative standing. So what's the basic idea here? It's actually a little bit different than the approach from 3.1 and 3.2. At 3.1 and 3.2, we were looking at the data set as a whole and asking, can you provide me with a number that describes some characteristic of the data set as a whole? Maybe that describes what the typical data point is like in that data set, or maybe that describes how variable that data set is, something like that. In measures of position, we're zooming in a little bit and we're saying, for a specific data point in the data set, or data value in the data set, or even maybe hypothetical data value in the data set, where does that value or that point kind of stand relative to its peers in the data set, relative to the other data points? So where does a given data point or value, or hypothetical? Most of these questions that we're going to ask and answer, we could be using an actual data point that's actually in the data set, or we could say, well, for this data value, even if it's not a member of the data set, even if it's not associated with a specific data point, where would it fall if it were in the data set? So where does a given data point or value or hypothetical data point or value fall or stand in the data set? So here we're taking a look at one specific data point, data value, hypothetical data value, and asking where it stands relative to the other data points and data values. Our first attempt at answering this question or giving some kind of answer to this question is the z-score. And it's defined as follows: z equals x minus mu over sigma. So here x is the value associated with the given data point or the hypothetical data value. Mu and sigma, of course, being the mean of standard deviation. Or if we had a sample, we have a very similar calculation, just using different notation. So a couple notes on the z-score. The first thing that we might see right away is that it's actually unitless. X has units of the original data, of course. So does mu. Their difference has units of original data. And sigma also has units of original data. So those units divide out. So the z-score is unitless. That makes it pretty nice to work with. A second note is it might seem kind of minor importance in chapter 3, but actually starting in chapter 6, for most of the rest of the course, starting in chapter 6, just about every problem is going to use the z-score or maybe some close variant of it. So the z-score is almost ubiquitous in the material from chapter 6 through the end of the course. So this is actually much more important than it kind of at first looks like it is. And what is the z-score kind of saying? It's saying how many standard deviations above the mean is x. Let's look at a couple examples, and we'll kind of revisit this statement in the context of a couple examples. So remember our tax returns per day examples with Ashley and Brandon. Remember the mean was 8 for both, and Ashley's standard deviation was 2, while Brandon's was 4. So maybe I'm looking at the Ashley data set, and I'm curious about Ashley's best performance day 11. So maybe I'll write x sub a for Ashley equals 11. And I'll compute the z-score for this. So z is 11 minus, we need Ashley's mean, which was 8, divided by Ashley's standard deviation, which was 2. So that's 3/2, or that's 1.5. Z equals 1.5 tells us that 11 is 1.5 standard deviations above Ashley's mean. So 1.5, or sorry, 11 is a 1.5 standard deviation event, a 1.5 sigma event. It's an event that we might say is maybe a little bit unusual, but not at all surprising or striking. Let's take a look at the Brandon data. Let's look at Brandon's best day. What's the z-score for Brandon's data value 14? So we take 14 minus Brandon's mean of 8. Brandon's mean is the same, 8. But Brandon's standard deviation is 4. We get 6/4 or also 1.5. So 14 is 1.5 standard deviations above Brandon's mean. So even though Brandon's and Ashley's means are the same, their standard deviations are different. So going 1.5 standard deviations above the mean is results in a different data value for the two of them. If instead I was to look at Brandon's data value 11, say this one, Z is going to be 11 minus 8 over 4, Brandon's standard deviation, or that's 3/4 or 0.75. So for Brandon, we would say something like 11 is 0.75 or 3/4 of a standard deviation above Brandon's mean. We could also look, for instance, at Ashley's data value, maybe 7. So for Ashley's day that she got 7 returns completed in that day, her z-score for that day would be 7 minus 8 over the standard deviation for Ashley of 2, or that's negative 1/2. So we can say that 7 is 1/2 of a standard deviation. Well, a negative z-score means that we're below the mean, right? It's 1/2 of standard deviation below Ashley's mean. So the negative z-score means that we're below the mean. And then the numerical part tells us how many standard deviations we are below the mean. And lastly, just as a last example, we could ask a question like, I guess I'll come down here so that these stay kind of together. If Brandon had gotten, or maybe in an upcoming week or something, if he ends up with a day where he gets 6 returns that day, note that that's not a member of this data set. So what about a hypothetical data value? What if he got 6 returns per day? What would the z-score be associated with that be? Well, I can compute it just the same. 6 minus 8 over 4, subtract Brandon's mean of 8, divide by his standard deviation of 4. There's nothing wrong with this, right? There's nothing, nothing is broken or anything by using 6, even though we don't see a 6 explicitly in Brandon's data set. But this gives me negative 2 over 4, negative 1/2. So 6 is 1/2 of a standard deviation below Brandon's mean. We could we could ask a question like what data value is so many standard deviations above or below the mean, and that's essentially the question that we were asking up here. We were constructing these boundaries, right? So really we were just looking at what proportion of, and the empirical normal rule, for instance, what proportion of data points have a value that's associated with a z-score less than 1 in absolute value. So this is just absolute value of z less than 1. Or these, I got my colors all backwards here, but absolute z less than 2, right? The within 2 standard deviations of the mean data values are just all of those values that have a z-score less than 2 in absolute value. And of course, for the three sigma interval, that's just absolute value of the z-score less than 3. So we could rephrase or reframe our empirical normal rule in terms of z-scores, and we see that there's a very close connection here between the two. And we could, of course, reframe Chebyshev in a similar manner if we wanted to. The z-score will turn out will be, the empirical normal rule associated with the z-score will be a much more natural association, but we could reframe Chebyshev if we wanted to. Any questions on z-scores? Computation is not that difficult. And, at this point, it might not seem all of that groundbreaking, but again, it becomes very important later in the course. Okay, let's come down here and look at percentiles. So let me bring I'm random data down. Okay, so what is the idea of a percentile? I think most of us have probably seen percentiles before reported. And a lot of times we see them in the context of maybe a test or something like that. You take a standardized test for like for graduating grade school or high school or something like that. And typically they'll return to you a score, maybe a score that, you know, has some units associated with it or whatever. Or maybe you take the SAT and they say your score is, 1270 or something like that. And you're like, okay, well, wonderful, I got a score, but what does that mean, right? Really what you want to know in a standardized test is really how you performed relative to your peers. Did I do better than most folks? Did I do worse than most folks? Did I do kind of in the middle? Did I do better than almost everybody? Um, that's kind of what you want to know. And that's what a percentile is kind of trying to tell you. So to say that a data value is, say, at the pth percentile means that data value is above p% of the other data points values and below 100 minus p% of data points. So in other words, if I say you took this exam, you got this score in the exam, typically that score, I mean, maybe on a classroom exam, things are on a percentage scale so that, and we kind of know how other students tend to score in exams, like, it tends to be a lot of B's and C's, not so many A's and not so many D's or F's. So we kind of have this like mental picture of just if I know what score I got in an exam, I know if that's good or not. But for something like, say, an SAT, you get a number, 1160, and you're like, okay, well, what does that mean? But if it says you got an 1160 and you're at the 72nd percentile, that means you did better than 72% of other test takers and you did worse than about 28% of other test takers. So we have a couple of things to note about the percentile. Number one, if we don't have very many data points, like if we have a data set of size 5 or 10 or something, we can't really say this data value is above p% of the other data points and below 100 minus p% of the other data points. That kind of like, if I say you're right at the 50th percentile, so that means you're above 50% of the data and below 50% of the data. Well, that like kind of squeezes you out. That leaves you no room, right? There's 50% below you and 50% above you. That's like everybody, but where do you sit, right? So we always have this little issue of how do we resolve that? This would be the ideal up here. If we had infinitely many data points, this would be a perfectly fine way to go about it. But we don't. Or even if we had lots of data points, even if we had a few hundred data points, if you're plus or minus, a tenth of a percentage point or a third of a percentage point or something, it's probably not a big deal. But when we have small data sets like these, n equals 5 or 10 or something, we have to make some decisions. So the way that I approach this, I think, is consistent with the statistical principles we've talked about before. The book approaches it slightly differently, and I'll discuss that in a little bit here. But let's take a look at the Ashley data first. Let's let me just make a copy of this down here, and we'll just get rid of the Brandon data for now. I think I can just delete this row or this column. There we go. So we'll look at just the Ashley data for now. So the Ashley data set of size 5. We note that everything is in order already. And that's quite important, right? If I'm interested in how many folks that I do better than or worse than, there has to be a natural ordering or ranking here. I need to be able to place either test takers in order from lowest score to highest score, or days in order from lowest performance to highest performance, or something like that. So there's a natural ordering ranking here, and we've already put our data in order from lowest to highest. Now, what is my goal with this? My goal when I'm trying to describe something as a percentile is to chop up the interval between 0% to 100%. I'm trying to chop it up and kind of allocate chunks of that interval to different data points. That's really my goal. And I think that for anything under 10 or to anything 10 or below on a sample size, the easiest way to do this is visually. So we're just going to draw out a number line here from 0% to 100%. Now I note that I have n equals 5 data points. So what I'm going to do is I'm going to come along here and I'm going to think of 0% as 0/5. And I'm going to think of 100% or 1 as 5/5. And I'm going to count by fifths, 0/5, 1, 2, 3, 4, 5/5. So I need 4 tick marks equally spaced in here. Draw them more or less equally spaced, don't have to be perfect. Mine are certainly not perfect. And these will be at the fifths. So 1/5, 2/5, 3/5, 4/5. Feel like I'm saying something from Dr. Seuss or something. 1/5, 2/5, red fifths, blue fifths, or something. I don't know. But if I count up by the fifths, I see that I now have divided this interval from 0 to 1, or 0% to 100%, into 5 subintervals. 1 here, 2, 3, 4, 5, that are demarcated by the fifths. I can work backwards from these fractions, and I know that 1/5 is 20%, 2/5, 40%, 3/5, 60%, and then 80% for 4/5. So by doing this, I've divided my line, my interval, from 0% to 100% into 5 subintervals, 5 chunks that are of equal size. Now what I want to do is I want to take my data set, I want to take my data points, and I want to put their values in from lowest to highest. So 5 is the lowest. It's going to go in the leftmost bin here, or the leftmost. I think of it almost like property that, is to be owned by these folks. Like we have a city block here, and, number 5 gets the property that's from 0 to 20%. Number 7 owns the property from 20 to 40%. Number 8, that data point or that data value owns 40 to 60%, 9, 60 to 80%, and 11, 80 to 100%. So we've kind of allocated each of these folks to kind of their land or their property. Now, there are 2 types of questions I might want to ask when I'm dealing with percentiles. One question is really straightforward at this point. So I can ask, what data value is associated with a certain percentile. Maybe, for instance, the 72nd percentile. Maybe I say I have some money to give out for scholarships and I want to offer scholarship money to anybody who scored at or above the 72nd percentile on this particular exam. Maybe 72 is my favorite number. So that's why I picked this. Who knows? Well, what do? I just look at the 72% point here. I note that it falls in the 60 to 80% territory. Since 72% falls in the 60 to 80% territory, and that's kind of owned in a sense by 9, my answer is just 9. This is really just a table lookup at this point. So this is the value 9, or if we wanted to include the unit, 9 returns per day. So 9 returns per day is associated with the 72nd percentile. Or I could ask what data value is associated with the, maybe 45th percentile. Well, again, I see 45% is between 40 and 60%. That's squarely in 8's territory. So that's 8 returns per day. Now, kind of unfortunately, we have some strange cases that come up. What if I ask what data value is associated with the 40th percentile? Well, here I notice that I am exactly on the boundary between two territories. I'm like right on the fence line between 7's property and 8's property. And what I end up doing is I average the two. 7 plus 8 over 2, or 7.5. This might seem kind of like a funny thing to do. We're going to talk a little more about this in just a minute here. So if we're squarely in one property, so to speak, if we're like at 50% or 75% or at 89% or something like that, then we just grab the number that owns that territory, that's associated with that territory. If we're right on the boundary between two territories, which I didn't draw that very well, but you get the idea. If we're right on that boundary, if we're asking what data value is associated with the 60th percentile or the 40th or the 20th in this case, then we just average the two neighbors, the two owners to either side of that boundary line. So that's one kind of strange thing that can happen. We can resolve that pretty easily. Another strange thing that can happen is a little more philosophically strange. If I ask what data value is associated with, let's say, the 65th percentile, well, I see that would be 9. Or the 70th, well, that would be 9. Or the 61st, well, that would be 9. Or the 79th, well, that would be 9. There's a lot of percentiles that have the same data value associated with them. If I was looking at a graph, this isn't a histogram or anything like that. This is a regular old math graph. If I was to look at the percentile as the input, so this number here is an input. This is like a function, right? I have these as inputs, and then for each of these, I yield a unique output. So I have like 0, 20, 40, 60, 80, and 100. And then the associated value, where are my values? 5 to 11. So let's make this 5 and this 10. So from 0 to 20, roughly, I'm at height 5. If I ask what data value is associated with blank percentile, for any percentile strictly between 0 and 20, I would give the answer 5. If I jump up to a number strictly between 20 and 40, I'm up to 7. From 40 to 60, 8 is the output. So I have a piecewise constant function, or what we often call a step function. The steps are kind of uneven here, and then we go up to 9, and then 11. So our step function looks something like that. My tick marks are a little wonky, but all of these steps should be equal width, but the height deviation might be a little different. We also said that when we're at a boundary point, say at 20%, we like average the two. So really we have like open dot here, open dot there, and then a point that fills in right in the middle. Open, open, fills in the middle, and so on. We'll leave this and this as open dots, and we're actually not going to define a 0th or 100th percentile. Okay, so we might look at this and think, well, this is kind of unsatisfying. It seems kind of strange for me to say that the 61st percentile is 9, and the 65th is 9, and the 70th is 9, and the 75th is 9, and the 79th is 9, but the 80th percentile is 10. It all of a sudden jumps. And then the 81st percentile is 11, it jumps again, and then it stays 11 from like 81st percentile all the way up to 99th percentile. So that seems a bit strange. We can, and this is an aside, we can choose to smooth out that jumpiness, that very discrete nature that we like do nothing, do nothing, do nothing, and then jump, and then do nothing, jump again. We can smooth that out with something called interpolation. Excel will actually do that. So if you ask Excel to do these kind of computations for you, it will use something a little more sophisticated. It'll do something along the lines of like looking at, say, a point that's at the midpoint of each of these lines, and then connecting them with just a linear function to connect them. It'll do something like that so that you kind of have a gradual increase in data value as you increase percentile, right? So it's more gradual that way. Is there a particularly good reason to use a linear interpolation? Well, no, that's not a good or a bad choice. It's just a choice that they made. So you have to make a choice here. And at least to my knowledge and to my understanding, there is no good choice. It's just how you feel like doing it, as long as you're clear about how you do it and you understand the impact that that choice makes on what you're reporting. So Excel does it a more sophisticated way. Now we might want to ask the question in reverse. We might want to ask an inverse question. Maybe I'll draw this in green. Yeah. I might ask a question like, what percentile is associated with a certain data value, maybe a data value of, let's pick 8, for instance, of 8 returns per day. This is kind of what the SAT score does, right? They say you got this score based on which questions you got right and wrong. That's the score you get. And then they answer the inverse question, what percentile does that associate with? They take your score and everybody else's scores, they line them up. And then for each one of those, they say which percentile is associated with this score, that score, or your score. So for the data value 8, what percentile is associated with it? Well, we see, for instance, pretty clearly here for the data value 9, there's lots of percentiles associated with it. Same with the data value 8. This is the data value 8 here. There are lots of percentiles kind of associated with the data value of 8. Or in other words, if we're trying to invert this function, it's not 1-to-1. There are lots of inputs that can yield the same output of 8. It doesn't have a unique inverse. but I really want to answer this question. I need to make a decision. When I have an ambiguity like this, how am I going to resolve it? And again, that's a question that's a decision I have to make. Just like previously, I had to make the decision to use a step function instead of maybe what Excel would do, a linear interpolation, or maybe a more sophisticated stats package would do, maybe some other kind of interpolation like splines or something like that. I need to make a decision here how I'm going to approach this. Now, something I notice about 8, I might notice that 8 is actually the middle number. It's actually the median. And by definition, we'll see in a couple minutes here, the median is by definition the 50th percentile. It would really bug me if I somehow said that the percentile associated with 8, the median, is the 40th percentile here, but then later on I say that 8's the median and it's the 50th percentile. That will be internally inconsistent. Um, so I think what I'm going to do is it probably makes sense in some sense to make a choice that is consistent with this definition. On one hand, I know the median's 8. On the other hand, I know the median's the 50th percentile. And I might actually notice that that's exactly the midpoint of the interval that is in some sense kind of owned by 8. 50% is smack in the middle of 40 to 60%. So when I have to invert this function, I'm going to pick the middle of the interval that yields that same output. So I'm going to pick the middle of 40% to 60%. I'm going to do 40 plus 60 over 2 is 50, 50th percentile. So I'll say the data value 8 is at 50th percentile. Now, a couple of notes on this. Number one, if you read your textbook gives a very mathy way of computing these. They give lots of formulas. And honestly, I think the formulas they're complicated enough they confuse me. It's like there's this multi-step process, and at one point it's like, okay, if you do this and you get a whole number, you do one thing, and if you get a decimal after it, you do another thing. And um, you know, if we were trying to program this in, Python or something like that to handle data sets of size 10,000, yeah, we would have to really buckle down and understand that and, do that all very carefully, very formulaically. But we're trying to get a grasp of of what percentiles are. That's really the goal of this course overall, is to understand these things a bit deeper than surface level. So if that's my goal here, um, and I'm only working with manageable size data sets, maybe 5 to 10 data points, maybe even 20 data points wouldn't be so bad. I can just do this graphically. I think that's the much better way to do it. So I'm using my little graph here to help me answer these questions. And I'm using some intuition as well to kind of resolve these potential ambiguities. So if I ask what percentile is associated with the data value of 8, I would say the 50th percentile. Now, the other thing to note is how can I get this? The percentile is number of data points with value less than 8 over n. So this is what your book would say. And this would give, what's the number of data points with values strictly less than 8? 5 and 7, that's 2. Over n is 5. That would be the 40th percentile. That would be 40%. So really all that we're doing here is we're adding on plus 1/2 number of data points with value equal to 8. So we're doing 2 plus 1/2 times 1, or 2.5 over 5 is 50%. Right. we're basically saying, well, if we want to say how much property is below 8 versus above 8, if I just look at this property over here that's below it and say maybe for instance this property that's above it, I've kind of left out 8. I've left out all of 8's property. What's the downside of that? Well, if I think of it now, this actually data set is a population, but if I imagine that this was a sample, is that going to be a good estimate of the population value? Well, if I'm always choosing the leftmost endpoint of the land, so to speak, owned by a certain data value, I'm probably going to have a statistic that's biased to the left, or vice versa. If I was instead, I've seen other stats books make this choice, well, always going to the right. So they would say number of data points with value less than or equal to 8 over n. Well, then I have a bias statistic to the right. And our textbooks make this huge deal about bias and that we don't want bias statistics. We make sure to divide by n-1 in the sample variance. Everybody does that. Like they make a big point of that and harp on that. It seems kind of silly to me to define percentiles in a way that creates a bias one way or the other, and especially when resolving that isn't really all that complicated, either formulaically or certainly not graphically. We just pick the midpoint of the land, so to speak, that's owned by 8. Okay, so now let's look at the Brandon returns and do something similar to that data set. Again, I have n equals 5, so we'll get a little more practice going through a very similar scenario. I start off with my list of percentiles, essentially, my interval from 0% to 100%. And I remember that 0% is 0 fifths and 100% is 5 fifths. And I need to count up 1 fifth, 2 fifths, 3 fifths, 4 fifths. And then I'll go back to percents. 1 fifth is 20%, 40, 60, and 80%. Now, as a side note, when you get better at doing this, when you get more comfortable with this, you can just say, okay, 0 to 100% split into 5 is going to be 20 percentage points for each chunk of land, so to speak. So I know the first one's is going to be 0 to 20%, and then 20 to 40, 40 to 60, and so on. So you don't have to do the whole to fractions, count those out and then back to percents every time when you get more comfortable. We're in order. So we always want to check that, but our data set is in order already. And we'll just pop our data values in here. 3, 5, 7, 11, and 14. Again, from smallest to largest. And we can answer similar questions about the Brandon data set. Right, what data value is associated with, say, the 87th percentile? Well, I noticed that that is in the 80% to 100% bin or range or uh, property, and that's owned by 14. So 14 returns per day is data value associated with the 87th percentile. What percentile is associated with, say, the data value of 3, we wouldn't want to say 0 here. We wouldn't want to say 3 is at the 0th percentile. We really like to stay away from saying that something is 0 or 100%, really anytime we talk about percentages. But for a data value of 3, I see that it kind of owns all the property from 0 to 20%. I'm going to go with the midpoint, 10%. Right? That's going to be the unbiased estimate. That's also going to be the one that's consistent with the median being 7. And if we ask what percentile is associated with the data value 7, we would indeed get the 50th percentile. And we could ask, say, what data value is associated with the 40th percentile. I noticed that the 40th percentile is right between two properties, 5 and 7, so I'll just average those two. 6 returns per day there. Any questions so far? And I didn't grab my salary data. I don't think I have it up here either. So let me pop back to a previous one and grab my salary data. There we go. Oh. Okay, let's take a look at our salary data. And here I'm going to cheat a little bit. I'm actually going to get rid of this 30 data point here if I can select it. Delete row. So this is altered from before. I just got rid of that so that we can see an example with an even number of data points. So we have our slightly altered salary data, 25, 328s, 55, and 100. And let's do a similar thing here. Let's set up our kind of visual representation of the percentiles and then answer a couple of questions about it. As an aside, I mean, I'm just kind of coming up with these questions off the top of my head. I'm not like looking at this problem and deciding this is the reason I want to ask about the 87th percentile. I'm just picking different ones, just in case you were wondering. Okay, so our slightly altered salary data, this isn't exactly the same data set that we were using in the previous couple of sections. So I have 0% to 100%. I see that I have n equals 6 here. So I think of 0% as being 0/6, 100% as being 6/6, and I need 1, 2, 3, 4, 5/6 in the middle. 1/6, 2/6, 3/6, 4/6, and 5/6. And I might notice that, I'll put it in red maybe, the 3/6 is exactly 50%, right on the nose. The others will be approximate. 1/6 is about 17%, 16.6 repeating. 2/6 is 1/3 or about 33%. 5/6 is like 1 minus 1/6 or 100% minus 17%, or we'll call it about 83%. And 4/6 or 2/3 is about 67%. Right? Or we could think of it as 100% minus 33%, 67% or so. Importantly, I forgot to note, but these are ordered already. So check next to that. These are already put in order from smallest to largest value. Right. there are so many things we do that either completely rely on the data being ordered or are very just made very uh, a good bit easier or less error prone or whatever by having them ordered. That's why I always say just anything you're doing, even if you're just doing a measure of center, just put the data in order. It's just a good habit to get into. But we see that we're in order here. We see we have 6 data points. One thing we actually note here is that we have a couple of data points that have the same data value. And we're going to handle that a little bit differently than we have before. But we still, this 25, this first data point, its value gets that first lot, that first little bin there. Each of these 28s gets its own lot. So this first 28 gets this one, the second 28 gets that one, and the third 28 gets that one. So note that we didn't say like there's like 4 distinct data values, so we only split this 4 ways. No, we split it 6 ways. The data value 28 actually gets allocated 3 lots, 3 consecutive lots. And then 55 and 100. Now you can maybe see a bit of the silliness of if we took the left endpoint, 28 is simultaneously the median, but then if we said what percentile is associated with 28, we'd be saying the 17th percentile. That seems very strange. And in fact, you could imagine a data set consisting of all of the same data value. If we just had 6 data points that all had value 28, all of our data is 28, but we'd be saying that 28 is the 0th percentile if we did it at the way that the book does it. So it's a bit silly to do it that way. I don't know why they do it that way. Maybe I should email the author. I've emailed a couple of authors before and actually have gotten responses. Like I was really surprised. I'd point out, oh, I think this is wrong in the book or something, and they, email me back. So maybe I should email Triola and see if he emails me back. But his isn't the only book that I've seen do this. So that might be his answer. It's just, well, everybody does it that way, so status quo bias, right? But anyway, so we can ask a question like, what data value is associated with a percentile of, oh, let's say 91st percentile. Well, the 91st percentile is here in the 83 to 100 range, and that indicates a data value of 100. We could ask what data value is associated with the 50th percentile. I actually noticed the 50th percentile, because I have an even number of data points, that's right in the middle of the lowest 3 and the highest 3, right? But it actually turns out that on either side is just 28. So of course, averaging 28 with itself just gives me 28, which is the median. That's what I would expect from finding the 50th percentile, and that's what I get. If I were to ask a question like, what data value is associated with a 67th percentile, this would be kind of an annoying question to ask. Like this isn't the kind of question I would put in an exam or something. Because on one hand, you want to say, oh, 67%, I just look at it and average 28 and 55. But on the other hand, you're like, well, but really, this boundary here is really 4.6. So it's kind of like 66.7. So I guess 67 would be just a touch into the 55s territory, and we should pick 55. That would be kind of an annoying question to ask. And, I think there would be more than one reasonable way to resolve it. But I would, if I was being pedantic, I would probably say if you wanted to ask what's the 67th percentile, this is really like this boundary is really 66.66 so on percent. So I would probably say 67 is just a touch to the right of that squarely in 55's territory, but only by a tad. Right. And that is one of the downsides of not doing some kind of interpolation. Right. just a tiny increment in the input can cause a substantial change in the output. So that's one of the downsides of doing this, but to do something even like a linear interpolation, the math is sufficiently complex that, it would take us a full class period or two to explain it all and everything. And, honestly, it's just not worth that. Okay, we could ask a question like what percentile is associated with a data value of, say, 55. And again, here, I wouldn't be too pedantic. I would just take 67 plus 83 over 2, or that would be like 9/6 over 2. Um, so that's what, 75%. So 67 plus 83 over 2, 150 over 2 is 75. It's the 75th percentile. Right smack in the middle of that one. Now, what if I ask the question, what percentile is associated with a data value of 28? Well, 28 is in a couple different places. Now, keep in mind, though, if I'm respecting the order, the same data value, if it occurs more than once, will always be kind of contiguous with one another, right? So the three properties that are owned by 28, so to speak, really just kind of come together and make one big property. So the visual way to think about this would be to say, okay, the left boundary of 28's property is 17%, the right boundary is 67%. We're just going to take the midpoint. So 67 plus 17 is what, 84 divided by 2, and that's 42. That is right here, the 42nd percentile. And as an aside, this whole idea of properties being contiguous and all of that, that doesn't get any simpler under Triola's formula, because you have to think of the contiguous properties when you're taking the leftmost endpoint for all of those properties. So I, I think the trade-offs are worth it too, uh, to get more accurate, unbiased answers that are consistent. Maybe I shouldn't say more accurate, but to get unbiased answers that are more consistent with other things that we discuss in the book. Any questions so far on percentiles? So as a note, I think I mentioned it up here at the beginning. Actually, I didn't mention it, but there is in the supplemental materials folder, there is material posted for chapter 3, and there's a supplement on percentiles wherever it is. There's a supplement on percentiles, section 3.3, with some extra practice problems. So I know this isn't always the easiest material, so there's an extra supplement posted there. You can go through that. You can take another read through it. It kind of outlines the graphical technique and all of that, and then do a couple practice problems if you'd like. Any questions on percentiles? So a lot of the complexity of percentiles comes from trying to resolve this ambiguity of this function kind of being in some sense naturally a step function. Do we want to interpolate or not? Again, if you try to have Excel do this for you, it's going to interpolate. It's going to give you an answer that's not consistent with what I'm giving you here or with what the book is giving. So and this function is also not one-to-one. So doing the inverse problem, asking what data value is associated with a certain percentile is the forward problem. But if I'm trying to go backwards, if I want to say what percentile is associated with this data value, there's a range of options for the inverse problem. And we have to kind of make some decision on how to handle that. but at least the decisions we're making are ones that are motivated by not contradicting other statements. Like, for instance, we compute the median this way, and we define the median to be the 50th percentile, so we want those two to be consistent, things like that. Okay. Okay, so let's move down to a discussion of skewness and outliers. So the Pearson coefficient of skewness is defined as follows. It's 3 times the mean minus the median over standard deviation, or 3 times mean minus median over standard deviation if we were dealing with population. And what's the idea of the Pearson coefficient of skewedness? So far, we've looked at 2 different ways to determine skewedness, maybe 3 different ways. Kind of fundamentally, skewedness is when we have data points that are outliers and they tend to be on one side of the data set. So that's kind of just, one way of looking at it. Do you see a bunch of outliers that are, say, higher than most of the data, or a bunch of outliers that are lower than most of the data, and no outliers on the other side to balance them out? The next way we discussed looking at skewedness was really looking at the graph, right? So looking at the maybe a histogram, and if we see a cluster of data or a frequency altogether, and then we see a couple of points way off to one side, we might look at that as evidence of skewedness. Then we had something a little more objective. We looked at our measures of center and we said, well, between the mid-range, the mean, and the median, the mid-range is affected most by outliers, the mean next most, and the median essentially is unaffected by outliers. So if I see a certain ordering, say, for instance, that the mid-range is much larger than the mean and the mean is much larger than the median, that might be evidence in favor of some right skewedness. It's a little more objective, but we do have to say, what do we mean by substantially greater than? So here we have Pearson coefficient of skewedness, and this is going to give us a completely objective metric to assess skewedness. Now, is it perfect? No, I don't think so. Can you come up with strange data sets maybe where most people would say the data aren't skewed and Pearson coefficient says it is, or vice versa? Probably. But skewedness is a little bit of a fuzzy kind of slippery concept. So, but this is at the very least completely objective. You might disagree with it from time to time, but everybody computing this would come to the same conclusion on the basis of the Pearson coefficient. Then you can debate whether you like the result you got or not, right? So, here is the criterion: is if the Pearson coefficient is bigger than 1, then there's evidence of, well, Pearson coefficient bigger than 1. What would give a big Pearson coefficient? Standard deviation is positive. We have number 3. If the mean was much bigger than the median, that would make my Pearson coefficient a large positive number. When my mean's bigger than my median, that's indicative of right skewedness. On the other hand, if the Pearson coefficient is less than -1, what would give a large negative number if mean is much less than the median? That's evidence of left skewedness. And if the Pearson coefficient is in the interval -1 to 1, there's a lack of evidence of skewedness. So we compute our Pearson coefficient up here. We get a number out of that, and we ask, is that number bigger than +1? If so, that's some evidence of right skewedness. Is it less than -1? If so, that's evidence of less skewedness. And the only other option is it's between -1 and 1 inclusive. That would be lack of evidence of skewedness, that the mean and the median are close enough together that we're not really willing to say that they're far apart. Now, what is the Pearson coefficient being compared to 1 kind of saying? Let's just look at the right skewed example. This being bigger than 1, that's equivalent to I can multiply by standard deviation, divide by 3. So really the Pearson coefficient is just setting in stone, what do we mean by substantially bigger than in the measure of center comparison? When I say if the mean is substantially bigger than the median, well, substantially bigger than means more than a third of a standard deviation. If the mean is more than a third of a standard deviation above the median, then we say there's evidence of right skewedness. If the mean is more than a third of a standard deviation below the median, we say there's evidence of left skewedness. And if the mean is within a third of a standard deviation of the median, remember we kind of think of the median as being like the anchor and the mean getting kind of buffeted around by the outliers. But if the mean is within a third of a standard deviation of the median, and then lack of evidence of skewedness. So that's really what the Pearson coefficient is saying down here. It's really just taking that same idea from measure of center lining up a certain way, getting rid of the mid-range, just comparing the mean and the median, and saying substantially greater than or less than means more than a third of a standard deviation. Okay, any questions on that? So we don't have a completely objective way to determine whether there's evidence of skewedness, left or right. Uh, Although, like I said, it's not a perfect way, it's just completely objective. Everybody would agree that the Pearson coefficient says that this data set has evidence of right skewedness, or that data set doesn't have evidence of skewedness, but they might not agree on whether the data set is skewed or not. So this is kind of one metric that's used to assess skewedness, but it's not a perfect metric, but it has the benefit of being completely objective. So in this trend toward objectivity, skewedness is of course related closely to outliers. Now, if a data set is skewed, it has to have outliers by definition. So I can have a data set like this where I have most of my frequency clustered together and I have a couple outliers to the right. That's pretty clearly right skewed. I don't think anybody would disagree with that. So if there's skewedness, there must be outliers. But number one, if I say that my data set's right skewed, I know there's got to be at least one right outlier. But how many? Is this one an outlier? If there was one here, is that an outlier? Not really sure. On the other hand, if there are outliers, they could be kind of symmetric, right? These outliers over here are tugging X bar to the right, but these ones are tugging it back to the left. It kind of just stays in the middle right next to the median. So just because a data set doesn't appear to be skewed doesn't mean that there are no outliers. We could have outliers that are just kind of roughly symmetric, some high outliers, some low outliers. Or like I said before, even if we see skewedness and we know there's at least one outlier, we might want to ask, well, is that the only outlier? This one is, if we said this is right skewed, if these didn't exist, that one's definitely an outlier, but what about this one? What about that one? We would like an objective measure that that looks at each data point and can evaluate, is this an outlier or not? We don't want to rely on skewedness because, again, we could have symmetric outliers, in which case the thing wouldn't be skewed. Uh, and even if we did see skewedness, that really only tells us, that really only guarantees there's at least one outlier, but for all the other data points, we don't know whether they're outliers or not. So now we're going to look at methods for identifying outliers. The first one is a fairly simple one, and because of that, it's very standard. So if you've ever taken an experimental science course like chemistry or physics or something, it's quite often the case that they have you do some experiment, roll a ball down a ramp or something and time how long it takes to go from the top to the bottom. But you don't want to just do that once, right? Because your finger might have been a little wonky on the stopwatch or something, or maybe it ran over a little more dust or something in the middle than typical. So you might repeat that experiment and timing maybe 10 times. And you might get some results that aren't consistent with the other results. Maybe there was just one time that you kind of hit the button a little bit funny on the stopwatch and we're off by quite a bit. And so when you look at your data, if you're, say, doing an experiment like this, you'd expect it to be very similar from time to time. So you might look at your data set and say, well, anything that is a 2 sigma event, I'm just going to get rid of, because I think those are outliers. And in a tightly controlled experiment like this, I really shouldn't have outliers, right? So if I have a high outlier or a low outlier, that probably means that I just messed up my timing on the stopwatch, or maybe we got a little bit of goop on the ball before we rolled it down the hill or something, and that made it roll a little bit differently, something like that. So I think that's an extraneous variable coming into play, and that's why we repeat the experiment a bunch of times to um, try to get a handle on maybe what those extraneous variables when they might be influencing the system, and maybe try to remove those data points. So this is the context where a lot of this kind of two standard deviation method is used. And the idea is this: if a data point has value more than 2 standard deviations from the mean, aka has a z-score bigger than 2 in absolute value, either z is less than -2 or bigger than +2, then it is an outlier. We have our data set. We compute the mean and standard deviation for our data set. We compute the z-score for each data point. If we see any of them that are bigger than 2 in magnitude, less than -2, bigger than +2, we consider those outliers. And if we were doing a lab report or something, we might say we take any outlier data and we just get rid of it and remove it from consideration. Or maybe in another scenario, maybe the outliers are quite important to us and we keep them. What we do with an outlier when we identify it is a different matter. But this method would have us identify outliers this way. This has a huge benefit in that it's relatively simple, it's easy to understand. There are some detriments that we'll see next time. But let's look at the Ashley and Brandon data again. And let me start with the Ashley data here. And let's just compute a z-score for each of these. The mean is 8 and Ashley's standard deviation is 2. So 5 minus 8 is -3/2 is -1.5 for the z-score for the data value 5. 7 minus 8 is -1/2 is -0.5. 8 is just the mean, so 8 minus 8 is 0 over standard deviation is 0. 9 minus 8 is 1/2 is positive 0.5. 11 minus 8 is 3/2 is positive 1.5. There are no data points, no data values with absolute z bigger than 2, no outliers. If we look at the Brandon data, so let's start with 14. Brandon's mean is also 8, remember, but Brandon's standard deviation is 4. 14 minus 8 is 6. 6/4 is 1.5. 11 minus 8 is 3. 3/4 is 0.75. 7 minus 8 is -1, negative 0.25 when we divide by 4. 5 minus 8, -3, negative 0.75 after we divide by the standard deviation of 4. 3 minus 8 is -5 over 4 is negative 1.25. We actually see no outliers for Brandon. This might be surprising because Brandon's performance seems to be so much more variable relative to that of Ashley's. But if I have a histogram that looks like this, right? Are these really outliers? I mean, just kind of the whole data set is spread out more. It's not like I have a really tight cluster all right here where I have a ton of frequency there. And then I have a couple that are far away. It's kind of like everything is a bit more spread out. So Brandon's standard deviation is twice as high. The data is more variable for Brandon, but he still doesn't have any outliers. And in fact, actually has two 1.5 sigma events. Brandon actually only has one 1.5 sigma event. The other more extreme is just a 1.25 sigma event. So the Brandon data has no outliers according to the two standard deviation rule. Now, a little aside, sometimes three standard deviations are used instead. This is likely just due to the experience of your physics or chemistry prof or whatever experiment you're doing. Maybe some things are just a little more likely to get an outlier, and they don't want you sitting in lab all day long trying to get 25 data points so that you can end up with 7 of them that seem to work well or something. So sometimes two standard deviations is replaced by three standard deviations, but you can see that the ideas would be exactly the same. Okay, when we come back, we will do the two standard deviation method for salary data, and then we'll talk about some of the shortcomings of that method and develop a method that doesn't have those shortcomings, the 1.5 IQR method. So we are just about done with chapter 3. I know it's a huge marathon of a chapter, but we are nearly done with chapter 3. We'll finish up 3 when we come back. Let me stop the recording.